This is Lab 2, Motion of a Falling Object. The main question that this lab asks is whether the computational models accurately predict the motion, which is a falling motion in this case, of the object observed. This lab begins with capturing video of some object that is falling. In this lab, a black case was dropped from a certain height. The video is then analyzed through a program called Tracker. With the data extracted from Tracker, an observed model of the position versus time graph is created. Using some of the information found from Tracker, computational models are created by using Newton's second law, weight force, and drag force coded in Python. These models are also a graph that display position versus time. Comparing the three models on the same graph gives us the answer to our question. After comparing the experimental data and the model data by plotting them on the same graph, we can see that the differences are small. There is a small disparity in certain areas of the graph, but considering the scale of the axes, those differences are small. This indicates that the computational models do display an accurate representation of the object's motion. This lab utilizes the fundamental principle of physics, which is Newton's second law. From this law, we are given two equations. The first equation relates the final velocity to the initial velocity. Having a net force on the object will cause the final velocity to differ from the initial velocity. In our case, the final velocity will be greater than the initial velocity. The second equation relates the final position to the initial position. To calculate the net force, two equations are needed, the weight force and the drag force equations. All of these equations shown here will be used when constructing the computational models. The data that was extracted from Tracker is shown on the right. Only the time t and y column were used in graphing the observed model. The graph of just the observed model is shown above the data points. The clip on the left here illustrates how the data points were collected from the original video. The values shown on this slide are the values needed to construct the computational model. All of these values are used in the Python code. Net force is calculated by adding the weight force and drag force on the object. Those two equations were shown earlier. V here is the proportionality constant of the drag force equation. The time frame of the video came out to be 0.533 seconds. Here we see parts of the Python code used to construct the computational models. The picture on the top highlights the Newton's second law equations, the final velocity and the final position equations. The arrows show where in the code these equations are translated. The picture on the bottom highlights the net force, which is constructed from the weight force and the drag force. Again, the arrows indicate where in the code these equations are translated. When the code is run, these two models are constructed. The picture on the left shows the position versus time graph. As we can see, the object is not moving at a constant velocity. Rather, it is getting faster and faster as the time goes on. It is accelerating. The picture on the right shows just the ball's position. You can think of this as the illustration of the original video, the ball being dropped. The yellow arrow represents the weight force, and the small blue arrow on top represents the drag force. As stated in the beginning of the video, the differences between the models are small, which means that computational models display an accurate prediction of the object's motion. Between the two computational models, though, it appears that the model with both weight force and drag force predicts the motion better, especially towards the end. This is due to the inclusion of drag force in modeling the motion. If the object was initially thrown downward, as opposed to just dropped from rest, the terminal velocity in the case would be the same. Even if the initial velocity is greater than the object's terminal velocity, the object will slow down to reach that terminal velocity. In whatever case, the drag force will be equal and opposite to the forces bringing the object down. Between the two computational models, the model on the right predicts the terminal velocity. Only the model on the right shows the drag force acting on the ball. The drag force is the force that leads the object to reach its terminal velocity. As the drag force increases to reach the same magnitude as the weight force, terminal velocity will be reached. In this case, if the object stayed in the air for long enough, and the blue arrow was allowed to become equal and opposite to the yellow arrow, terminal velocity would be reached.